All right, so we're going to use the ratio test. So you're going to need to take a mental picture of this because I'm going to move to a different whiteboard. We're going to take the limit as n goes to infinity of the n plus 1th term divided by the nth term. And we're going to get a limit. If I can make that limit less than 1, then the series converges. If I find that the limit is always greater than 1, then the series diverges. If I find that the limit is exactly equal to 1, then there's something else happening and I have to make a different plan, use a different test. So I'm going to find the radius of convergence for the sum of n x to the nth over 10 to the n. In retrospect, when I write out the ratio test, I might put the absolute value bars in. What typically happens here is we use the ratio test to check for absolute convergence. So I'm going to take the limit as n goes to infinity of the absolute value of the n plus 1th term divided by the nth term. And just recall that when I divide, since it's pretty typical to have a ratio for every term, I'm going to need almost every time I use the ratio test to remember that to divide a fraction by a fraction, I can multiply by a reciprocal. So this is the limit as n goes to infinity. I'm going to use this expression, but everywhere I see n, I'm going to replace it with n plus 1. This is going to be the absolute value of n plus 1 times x to the n plus 1 over 10 to the n plus 1. I'm supposed to divide that by the nth term, which is this exact thing, but instead I'm going to change that to multiplication by the reciprocal. That's going to be 10 to the nth over n x to the n absolute value. I could have put absolute value bars around this guy, but he happens to always be positive. All right, so I'm going to jump up here, and I'm going to notice some things that cancel. If I look at the 10 to the n's, yeah, so let me consider this part. If I have 10 to the nth divided by 10 to the n plus 1, think about what that really means. That's like 10 to the 100th divided by 10 to the 101th. So however many 10s I have multiplied together in the numerator, I'm going to have one more 10 multiplied in the denominator. So I'm going to end up with a 1 over 10 is how those 10 to the n's are going to simplify. The n plus 1, and I can take that out of the absolute value bar because 1 over 10 is always going to be positive. If I consider now the n plus 1s and the n's, n started at 0 and is going toward infinity, so I can see that that's going to, I could write that as n plus 1 over n. I can take that out of the absolute value bars because n is always non-negative. And my situation for the x's is similar to what I had for the 10s. However many x's I have multiplied in the numerator, I'm going to have one less x multiplied in the denominator, which means I'm going to have the absolute value of x there. So now if I consider the limit, you'll find that sometimes you'll have to use L'Hopital's rule here, but I don't think we have to use L'Hopital's rule in this case. That's going to be the limit as n goes to infinity of the absolute value of x over 10. And think about what happens to n plus 1 over n as n goes toward infinity. That's going to have a limit of 1. So I've figured out that the limit of the absolute value of my n plus 1th term compared to my nth term is the absolute value of x over 10. If that expression is less than 1, then my series will converge. So that's what leads me to this last step. This is what you're going to start to really associate with the ratio test. Absolute value of x over 10 is less than 1. And we can write that without the absolute value bars by saying -1 is less than the absolute value of x over 10, which is less than 1. I can multiply by 10. I'm going to get -10 is less than absolute value of x. Now I don't need the absolute value bars anymore. That was the whole point. There we go. All right, x over 10, which is less than 1. So negative 10 is less than x, which is less than 10. So, and really I could have done that up here to get the absolute value of x is less than 10. I have found the radius of convergence. The radius of convergence is 10. I also happen to have found what might or might not be the interval of convergence. The thing I don't know here, the reason I haven't answered the question that we're going to address in 9.5 is that I don't know if this series will converge if x is exactly equal to 10 or exactly equal to negative 10. But I have found that negative 10 and positive 10, those are like the endpoints on my interval. I don't know whether they're included or not, but that's enough to tell me the radius of convergence is 10. All right, I'm going to find radius of convergence again. I have a new series, so I'm going to take the limit as n goes to infinity of the n plus 1th term divided by the nth term. Here I don't have a ratio, so I'm in my original series, so this is probably going to be easier to write. It's going to be n plus 1 factorial x to the n plus 1 divided by n factorial x to the nth. All right, so that's the limit as n goes toward infinity of what's going to happen to my x's. Oops, that should have been absolute value. Both cases. The absolute value of x to the n plus 1 divided by the absolute value of x to the n. I'm going to have one more x as a multiplier in my numerator than my denominator, so it's going to settle out to be absolute value of x. And then think about what n plus 1 factorial over n factorial means. We'll do this. If you already know about factorial notation, then don't worry about this part. But especially if it's new, think about what that means. For example, if n were 10, just as an example, that would mean 11 factorial over 10 factorial. So that's 11 times 10 times 9 times 8 times dot 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 over 10 times 9 times 8 times dot dot dot. So notice that everything here is going to cancel out except for that first number. So that's what ends up happening here, is that whatever n plus 1 is, that's going to be a multiplier, in my limit. And all the other multipliers cancel each other out, numerator and denominator. So now I have to think about what happens to this limit as n goes toward infinity. Well, check this out. It doesn't matter what x is. I'm going to multiply it by infinity plus 1. That has a limit of infinity. So this definitely has a limit that is greater than 1. And I can conclude then that this series has a radius of convergence of 0. It will converge at the exact place where x equals 0. But remember, that's the radius of convergence is like how far to the right or left of x equals 0 will this converge, and it will converge for no other values except, so radius of convergence is 0. All right, here's one more problem. I've modified it from a released multiple choice question. I want to find the radius of convergence of this series, so I'm going to take the limit as n goes toward infinity of, here, my original series, every term is a ratio. So instead of dividing a fraction by a fraction, I'm going to multiply the n plus 1th term, which is going to be x plus 1, to the, I used n here, they use k here, doesn't matter as long as I don't mix up the notations. This is going to be n plus 1 over n plus 1 squared. And instead of dividing that by the nth term, I'm going to multiply it by the reciprocal of the nth term. This is going to be n squared over x plus 1 to the nth. And I'm This should all be absolute value. There we go. And considering what happens to this expression is n goes toward infinity. So that's going to be the limit as n goes toward infinity. Let's see, some things I have to figure out. I'm going to have to compare. I'll change colors just to sort of organize my thinking. If I consider what happens to the x plus 1 terms, that's x plus 1 to the n plus 1th, and x in the numerator, and x plus 1 to the n, which means I'm going to have one extra factor of x plus 1 in the numerator. I don't know yet if x is negative or positive, so I'm going to have to keep those absolute value bars. And then think about what happens to n plus 1 squared and n squared. So I'm going to take the limit as n goes toward infinity. So that's going to be like, I could multiply out n plus 1 squared, but the term that's going to dominate in the denominator is the n squared term. The term that's going to dominate in the numerator is the n squared term. As n goes toward infinity, they're going to approach a ratio of 1. So the limit as n goes toward infinity of the absolute value of x plus 1 times 1. I'm going to need the absolute value of x plus 1 to be less than 1. That tells me that, well, that's enough right there to say that the radius of convergence is 1. I'm going to be able to solve that later to say negative 1 is less than x plus 1, which is less than 1. Subtract 1, subtract 1, subtract 1. And I get negative 2 is less than x, which is less than 0. But notice I'm going to get the same result either way. That's the distance across that interval, the distance from negative 2 to 0. That's like the diameter of convergence. I need the radius of convergence, which is 1, which is what I knew back when I was up here.